On equilibrium, and it's on acid-base equilibrium. Okay. Now, it's going to start out today very easy because it's going to be stuff. After this first board, it's going to be stuff that all the calculations that you've already seen before and you know how to do.
How difficulty level is this related to last chapter?
It's going to be continuing the same theme in a little bit. So, what you didn't, I think you probably understand. The better you understood that last chapter, the better you're going to do in this one, but you're going to see it multiple times. We got to do KC or solving for KC or solving for X. You're going to do that exact same kind of problem here, only it's going to be KA or KW. You're going to be using to derive that new constant right now. So this first board is new, but after this first board, what you're going to be doing is calculating pH and hydronium. Remember doing those in Chem 1. Now, that were not hard, and we did it. If it was a Chem 1 topic, and you were able to do it then, you certainly will be able to do it now. However, after today and tomorrow, with these first 2 days, then we'll get into the equilibrium part. All right, let's start off with acid-base equilibrium. Turns out that water by itself breaks up into hydronium and hydroxide ions just like that, in that equation right there. Okay? A water molecule will bang into another water molecule. One guy will lose an H, the other one will gain it. And it's happening all the time. Every now and then they'll bang back into each other. It doesn't happen to a great extent, very slightly. As a matter of fact, the amount it happens to, you don't have to write this down. We're going to talk about this later, is 0.000001 mole of these per liter of water. That's not a lot. It's an extremely small number. Don't write that down because we're going to get to that later when we get to the calculations. But look at that number. 0.000001 moles per liter of hydronium hydroxide ions. Very slightly does this do this by itself. Now I can make it do it more by adding an acid to it, or I can get more hydronium, or I can get more hydroxide, and that's what we're going to talk about. But right now I got to derive a constant which kind of goes right back to your bonus question on the last test we just took. That was a bonus question on that test. All right, and it was. I think the equation I used there was something like A to the A, B. Right. I use like A to the A, or AA plus BB yields CC plus DD. Now don't write this down. All right, but basically I asked you to derive that. No one got full credit on that because I didn't tell you it would be on there. See if anybody will actually be able to do it. And some of you tried it and you got some of it right. But basically, I'm going to ask you to do the same basic idea. Only for this one, it's a specific equation. It's not A, B, B. The A is 1. This is 1. The concentration would be for water or for hydronium, and the coefficients are 1 here. So how would you do the derivation of Kc? That's what I'm going to get to Kc and then beyond. How would we do the derivation of Kc using this equation? Well, the first thing you have to realize is that water, in the forward direction, if it's a one-step mechanism, the rate forward would equal Kf times water, right? If it was a one-step mechanism, that's correct. And in the reverse direction, what would the rate look like for that guy? You may remember doing this, only we used A, B, B. Here we're using actual reactants and products. In the reverse direction, what's it going to be? The rate reverse is going to equal Kr times hydronium and hydroxide multiplied together to their coefficients, which their coefficients are 1 anyway. So there you have it. We're going to continue. So this is what you would have needed to show on the derivation from the last one we just did, the extra credit one. It will not be extra credit on this test. This test, you will have to do a derivation. I'm actually going to derive a couple of things here. I'm going to derive Kw, I'm going to derive Ka, I'm going to derive Henderson-Hasselbalch equation. All of those things, one of them is going to be on the test, of those 3. Okay, well, let's finish this guy up. What happens after that? What do we know at equilibrium? Yeah, rate, not K, somebody wrote that down. At equilibrium, Kf does not equal Kr. The rate forward equals the rate reverse. That's the definition of equilibrium. Okay, and somebody did write that down. Kf equals Kr. That's not true. Remember, Kf over Kr is actually Kc. We're going to get to that in a minute. Yeah. That's all I need. All right, so if the forward and reverse rates are equal at equilibrium, then that also means, look here, this is equal to that, right? Agreed? It's the same basic idea. Yay. Notice what I did with the waters. Instead of having water times water, I have water squared. All right? What did we do next? You might be coming back to you now. Well, we brought the constants to one side, remember? And the variables to the other. So we brought the Kf over to this side, over Kr. Remember that? And then we brought the variables to the other side. So it looked like that. And of course, at this point, for you guys, back when I asked you that question, it would have been A to the A, I'm sorry, C to the C times D to the D over A to the A times B to the B. Products over reactants raised to their coefficients. We used that all last chapter, and we're going to use it kind of again this chapter, but that was called what? What is Kf over Kr? Kc. It is Kc. So write down that's what equals Kc, or on either side, I don't care. But here is the new thing. In dilute solutions, as long as I don't add a huge amount of hydronium or hydroxide ions to these things, in dilute solutions, we're talking about water being virtually constant. I want you to think about this. If I have a dilute solution, don't have to write this down again, and I told you that number was 0.0000001 moles per liter. Think about it. Let's say I have, 4 moles of water, 4.00 molar of water. All right? If that's all I get out of the hydronium, if I subtract 0.0000001 or even 0.0000004, all right, from that number, I'm going to get 3.9999999. Unless I have like 8 significant figures, it isn't even going to show up. So I'm basically going to ignore the fact that water's changing at all. I'm going to call him a constant. And I am. I'm going to bring him over here with the other constant of Kc. That's how I'm going to rearrange it, because in dilute solutions, the water concentration is virtually constant. The amount of hydronium and hydroxide you're actually getting, reacting with the water, is not going to really affect how much water, all right, you're not going to really diminish the amount of water you have. So I'll bring him over to the other side with Kc, and therefore it'll look like this. Kc times water squared equals hydronium times hydroxide. This makes it actually a lot easier. Why does it make it easier? There's no denominator. That's great. Why is that nice? Without a denominator, it's a lot easier to do the calculation. I mean, these are still going to have problems, but I'm going to show you even a trick we're using the quadratic formula. I mean, I've already shown you one trick, and I've let you use the calculators to do the quadratic formula. But I'm going to show you even another trick when we get to something called Ka. All right? By definition, Ka will be very, very small concentrations of hydronium or hydroxide ions, and we'll be able to make another assumption there. All right, anyway, that is Kw. Kw is Kc times water squared. Okay? Because the reason being, water is a constant if we're dealing with this equation where we have such a small amount of hydronium and hydroxide ions produced. You may recognize this, because if you don't yet, you will in a minute. Okay? We used it last year. But according to last period, and I have to accept them, that even though I couldn't believe I didn't actually call it Kw. According to last year, they said that, well, I didn't call it this, but they all remembered using it as soon as they got to the calculations. All right, let's do this. That's called the ion product constant of water, by the way. And then I'll show you where we're going to actually derive the actual numbers for it. Because we're not done with this. We've derived the Kw, but now I'm going to actually tell you what the actual number is. So this continues. Just continue this on. It just didn't all fit on one board here. We can actually derive what Kw is. He is a constant after all. So at a certain temperature, I know he will not change. And we're going to work around 25 degrees Celsius. So I'm going to talk about, at that temperature, what happens. In pure water at 25 degrees Celsius, the hydronium and hydroxide ion concentrations equal each other. And they both equal 1 times 10 to the negative 7th, which is 0.000001. I told you didn't write it down then because you're writing it down right now. All right, let's go back for a second. So what I'm saying is, at 25 degrees Celsius, these guys bang into each other. 1 mole of them would give you 0.000001 of this. And for every one of these, I'll get one of those. So that's why water's not basic and water's not acidic. You get the same number of hydronium as you get of hydroxide for each of these. So if I know that, I now know what Kw is. I know what Kw is because I can just plug that into my equation. Kw is hydronium times hydroxide. Plug the numbers in. 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. And what is Kw? You may recognize this as soon as it comes up. What's it? What is it? 1 times 10 to the negative 14th. You may remember using this equation from Chem 1. Hopefully you do, because even if you don't, I'm going to do 2 examples on the board right now anyway. You'll have a lot of time tomorrow to work on some more, and I'll be doing one backwards tomorrow as well. But these first 2 days, that's all we're doing is these easy ones. That's all the notes I have. We're going to do 2 examples now. Oh, I'm sorry, it's not all the notes. I have to review with you how to do pH as well. One more little board here of notes on pH. All right, so this is a special constant specifically for water. All right, and what I'm saying here is, and this will become clear in a little bit, since Kw is a constant, what's going to happen if I add an acid to this guy and I make that number higher? What's a higher number than 10 to the negative 7th? Negative 6, negative 5th. So let's say I have 10 to the negative 5th. I increase the concentration of hydronium ions. If this guy's a constant, has to stay at negative 14, what has to happen to that guy's number? That would have to be smaller, negative 9, because these guys are always going to have to add up to 10 to the negative 14th. That's why. He's a constant. They have to add up that way. All right. So we can calculate the hydronium hydroxide and be able, in that respect, calculate the pH. That's what we're going to talk about now, pH. By the way, pH is written small p, capital H. Big P, little h is as in Mr. Phillips, Mr. pH. He has a very acidic wit. He actually does that. All right, the pH. See, it was kind of invented by a guy who had to take hydronium ion concentrations all the time in a plant. I think it was a bottling plant for soda or something like that. And he, instead of writing down these numbers, which would have been 0.00000 whatever, or even times 10 to the negative whatever, he decided, I'm just writing down the exponent. I'm just going to write down the power to which 10 is raised, all right, and take the negative of it so it's not negative. So that's what the pH is. It's the negative common logarithm of the hydronium ion concentration. And that pretty much tells you what the pH is. It tells you how acidic it is, I should say, because hydronium ions are what makes something an acid. Now that's just I know that's a lot of ugly words to say something very fancy. It's just, a logarithm is just the power of 10 in a number. So it's just the power to which 10 is raised in the hydronium ion concentration. So for example, if I have 1 times 10 to the negative 4th power, what's the pH? That's the hydronium. That's what I know the hydronium is. What do I know the pH is? 4. pH is 4. If I know the hydronium is 0.0010 molar, what's the pH of that?
1.
No.
3.
3.
You have to move it over.
1.0010 is 1 times 10, 1.0 times 10 to the negative 3rd. So the pH is the negative of the power. The power is negative 3, right? But it's the negative of that. The power is the negative 3. Negative times the negative is a positive 3. This helps us understand why water is, what is neutral on the pH scale?
7.
Why? Because water by itself has 1 times 10 to the negative 7 moles per liter. What's the pH of neutral water? 7. pH would just be 7. Okay? All right, so that's what you'll be doing when you're calculating these things and using this equation right here. Although it's not going to stay that easy, you're not going to always have numbers that are 1 times 10 to the negative something power, because you'll have to use your calculator. Yeah, now some of you probably by now are starting to remember some of this, and if you don't, you're going to, as I do the first 2 I'm only doing 2 examples today.
Did you give us like OH last year?
I will. I'm going to give you. Yep. You're going to recognize all this. And the good news is you're going to find this to be much easier than what we were doing in the C problems, where you had to solve with minus x and plus x and all this stuff, and K, C and all this, and it took forever, and you had to use a quadratic formula. The reason these are going to be easier that I'm first starting out with today and tomorrow is because I'm going to deal with only strong acids and strong bases. And what I mean, and I said this last year, but I'm sure you've forgotten, by a strong acid or a strong base isn't just some acid or base that burns you worse. I'm not talking about a strong acid and a strong base by its concentration. I have a stronger concentration. 2 molar is stronger than a 1 molar. No. When we call something a strong acid or a strong base, it does not talk about its concentration. It's not talking about how bad it burns you. It's talking about how much it breaks up in solution. It is not an equilibrium problem. It goes to 100%. All right, I'll explain that. I'll just write that down first. Strong acids and bases break up or ionize completely in solution. They do not form equilibrium reactions. So a strong acid, like hydrochloric acid, goes 100% to completion. All of the hydrochloric acid you added to there reacts with the water. Okay? 100%. If I'm doing an HCl reaction, I will have an arrow that looks like that. I will not have an arrow that looks like this. Okay? Strong acids and strong bases, they go one direction and one direction, which is nice. And here's why it's nice. If I tell you I added 0.01 moles of your reactant, I know all of that became product. I don't have to worry about minus X and plus X. I don't have to worry about that. Okay? As you'll see. Now let's just do, I have 2 examples. Here's your first one. Copy that guy down. I'm going quickly because I want to be able to get this in and give you some time to work on some of the problems so that tomorrow when you come in here, you'll be able to do, I'll give you more time to work on it, but I'll be able to show you a different kind of problem, working backwards, and then give you more time to work on it, and then we'll do some new stuff. So I'm going to ask you to solve for 4 variables here, and so does the book, and so will I on the test. Hydronium, hydroxide, pH, and POH. And all I do is give you the concentration of the solution. And by the way, we've made these kind of solutions before. We've used sodium hydroxide solutions. You've made them up a bunch of times. You've used hydrochloric acid. Many times I told you this is a 1 molar solution, this is a 2 molar or a 6 molar solution. You now will be able to tell me what the pH of those solutions would have been. Now, we never worried about it at the time, but now you'll know. Okay? Now, first thing, if you remember back to those days, last year when we first covered this, you may remember that I had you show me the formula, the actual equation of what's going on, and I want that again. You're not going to get points in the homework if you just put down 4 answers, okay? Because you can look those up in the back of the book for any of the odd numbers. You're going to get points for showing me the equation and then the work for all of these guys. So let's take a look at the equation first of all. What's going to happen when sodium hydroxide is added to water? This is something we haven't done in a while. Sodium hydroxide looks like this. NaOHS, solid, right? I put him in water, 1 arrow going one way, H2O, dissolving in water. And do you remember doing this when we had guys breaking up in solution? What will I get when he breaks up in solution? You remember? Sodium ions, aqueous, and hydroxide ions, aqueous. Remember doing that? They just break up in solution into whatever the 2 ions are that held them together, or however many ions you have. Okay? Now, I'll talk about what would happen. You could tell me what would happen, I guess, right now, real quickly. I don't want you to change anything. But what if this had said NaOH3? What would be different? Na plus 3 OHs. You'd have 3 of them there, right? You remember doing that, hopefully, from Chem 1. Here's what's different. Do not write this down. Okay? Here's what's different. Don't write this down. In the last chapter, I told you 0.00100 molar was your initial. Please don't write this. You put 0 and 0. Minus X, plus X, and plus X. If, of course, this had been a 2 in front of there, it would have been plus 2X. At equilibrium, 0.00100 molar minus X, X, and X. And then we had to solve and note a Kc in order to be able to solve it. I don't have to do any of that anymore. none of this stuff is necessary because it goes to completion. If I put in 0.0010 moles of this, how many moles of Na am I going to get? 0.00100 moles. And how many OHs am I going to get? Same exact number. It's not like I have to worry about only some of that became and broke up into this. It all went that way. And there's no equilibrium. At the end of the reaction, you'll have 0 of this, 0.00100 of that, 0.0010, and that happens every time, which means I don't have to worry about it. In Chem 1, I never had to say this to you because in Chem 1, we had never gotten equilibrium calculations before. But I'm saying it to you now so you don't think you're going to be doing these equilibrium problems. I'm also saying this to you now because I know some of you will try to do these guys' equilibrium problems when they are clearly not. And you will know they're not because it'll say that right there. Strong acids, strong bases. If it's a strong acid or a strong base, it just goes to completion. So basically, if I have 0.001, this you can write down, I will get 0.00100 molar of this and 0.00100 molar of that. I don't really care about the sodium. He's a spectator in this whole thing. Because sodium doesn't make a guy more or less acidic or basic. I care about him. I care about the OH. Or I care about the hydronium for as an acid. Okay. Now, time to do the problem. You must write the equation out. And now, do we know any of those answers yet? Do we know hydronium, hydroxide, pH, or POH from just writing out the equation?
No.
Yeah. Who do I know?
The OH.
I know the OH. It's right there.
Oh, that's what it was.
Right? So I can just write down over here to the side, OH equals 0.00100 molar. I'm done with that. I know him. Who do I want to find next? I want to find hydronium. What am I going to use? Do I have an equation that relates hydronium to hydroxide from a second ago?
Yeah,
The Kw, right. So Kw equals hydronium times hydroxide. Which is nice, because now all I got to do is rearrange it. And by the way, when I rearrange this guy, I'm solving for hydronium. So hydronium is going to equal Kw over hydroxide, which equals 1 times 10 to the negative 14th molar squared over, let's put this guy into scientific notation. What's 0.00100 molar in scientific notation? 1.00 times 10 to the negative third, right? Why do I want to do that? Because this problem can be done without a calculator. I don't even need a calculator for this. What's 1 times 10 to the negative 14th divided by 10 to the negative third? When I divide exponents, what do I do with them? Subtract, right? So hydronium equals 1 times 10 to the negative 11th molar, right? Because negative 14th minus a negative third is going to be negative 11th. I don't even need a calculator for this guy, and I won't need a calculator for the rest of them either. Everybody got all that down so far?
Wait, negative 14 minus 3.
Negative 14 minus a negative 3.
Yep.
It's adding 3 minus the negative.
Oh, minus. All right.
Because you're dividing. That's what you do to exponents when you subtract.
How does H3 of them? 1 times 10 to the what? 11. Is that 11?
We've been saying it multiple times.
11.
Why is it 11? Hold it. Explain to me why it's 11 and how you would know that without having to ask it.
Oh.
Because 14 minus 3 is
Okay, well, negative 14 minus a negative 3 is a negative 11. Yeah, that's how you know. That's what you're doing in this problem. Okay, I now have two answers. I have hydroxide, I have hydronium.
All right, now I got to do pH.
Now I got to do pH. pH is negative log of the hydronium. Okay?
Well, you know the hydronium.
Exactly. The hydronium
Negative log.
is 1 times 10 to the negative 11. So it's going to equal the negative log of 1 times 0.00. So it equals a negative log of 1.00, or 1.00 times 10 to the negative 11 molar. So what does Now again, you do not need a calculator for this.
It's 11.
The answer is 11.
Why did we do it?
It's just the exponent.
Shut up, at least I know it's an 11.
It's just the exponent.
The pH just means a negative log of something. Logs are exponents. Exponent is negative 11 times a negative is a positive 11, right? Okay. And finally, do you guys figure out why I don't have to actually do a I could do for POH, plug in the hydroxide and do the same thing. But what will it always have to add up to, the pH of the POH? 14. Remember doing this?
No.
Some of you do. I see nodding heads. Others maybe not. So the POH is going to simply equal 14 minus 11, or what? 3. Now, I ask you a question at this point. Does it make sense that a sodium hydroxide, we all know sodium hydroxide is a base, right?
Right.
So it makes sense that sodium hydroxide, a base, would have a pH of 11. Yes, because pHs, 7 is neutral, right? 7 was neutral. And larger numbers of hydroniums would be smaller numbers because they're negative exponents. And higher numbers would be actually smaller concentrations of hydronium. As the hydroxide goes up, the hydronium goes down, and vice versa. That's how it has to be. All right, good enough. Now we're going to do one more, and I'm going to throw in a couple of curveballs here. Not to use any baseball analogies, because I don't want to be cheating.
Not all of us can have our quartz plowed.
Mm-hmm. We're still shoveling anyway.
Usually my quartz gets plowed.
All right. Same exact question. I just changed a couple of little things that's going to make the problem a little bit harder, because you're going to have 3 mistakes you'll really make here. 3 biggies that I see all the time. Okay, so let me point them out to you. You watching? Well, first off, the first mistake you're going to see is acids don't just dissolve in water like a base does. Somebody even asked the air class, it was to her, what do you call it? No, I was going to say, in her defense, she hadn't had chem, and she did not have it when I had double periods. It was 2 years ago. Like Dayton probably didn't have me either, and he probably didn't have it during double periods. All right, and Jesse, same thing. So he may not remember this as well, because I may have barely covered this back in the days when I didn't have double periods in Chem 1 every other day. I had to kind of fly through this and didn't really get to it very well. So they asked the question of, well, how do you know an acid from a base? Okay, now I hope everybody here knows how to know an acid from a base.
Hydrogen.
Yeah, right. Basically, all of your acids are going to be HCl or H2SO4. Now, that's not a perfect definition. There are some acids that don't look like that. But for the most part, your acids are going to be H something. And for the most part, your bases are going to be OH at the end of something, CaOH2 or AlOH3 or NaOH. There are some exceptions, one of them being ammonia, being a very common exception. But the difference is this. Your acids don't just dissolve in water. They actually react with water. So I'm going to write down H2SO4. And he doesn't just break up in water. He actually reacts with water to form hydronium ions. Watch what happens. What's the definition do you remember from the Arrhenius and Bronsted definitions of acids?
Oh, God.
Bronsted said an acid, you don't have to know Bronsted Arrhenius right now. You just have to know what they actually do. An acid donates H's. Remember, he gets rid of H's. He forms hydronium ions. So if he donates an H to that guy, he's going to make a hydronium ion. And what's going to be left over? The SO4 ion. Whoops, that's a -2. Okay? So he had 2 H's to donate, didn't he? He had 2 H's to donate. See it?
Yeah.
So to balance this out, I would have to have a 2 here and a 2 there. And so here's your second mistake. Remember, so the first problem is keeping in mind that acids don't just break up, but rather react with water. Second mistake, if you've got 2 H's, or if I had 2 OH's, or if I had 3 OH's, or if I have 3 H's, I've got to keep that in mind on the other side of the equation to balance it out. Okay? Now, the rest of it's the same. There's one more mistake coming, but the rest of it's the same. I start out with 0.00320 molar of that. Do I care about water at all? Because as long as I'm dealing with dilute solutions, it's not going to change. But here's a problem. I have to apply that to. 2 times 0.00320 molar for the hydronium. Again, I don't even care. I don't care about the sulfate either, right? Because he's not going to change the acidity.
We don't care about him. Done good.
No. All right. So now, everything here is going to be done backwards. Last time I was given the OH first. This time I'm given the hydronium first. Everybody see why I know the hydronium ion concentration now? What is the hydronium ion concentration? Yeah, it's not 0.0032. It's 0.0064, right? Because it's 2 times that.
Yeah.
0.00640 molar. See it?
Yeah.
That's the hydronium. Now I use when there's trouble, you call KW.
Oh, that's not funny.
I know.
Not funny though.
I thought you were supposed to call DLP or.
That's when you have an injury.
Oh, injury.
Injury.
Okay.
Oh, safe.
I smell bacon. Somebody's making bacon over there. Smell that?
It's my cologne.
Bacon is good.
Did you hear about that bacon?
Bacon batters?
No. You can get an app for your phone that wakes you up to the sound of sizzling bacon,
Oh,
and you
smell.
attach a thing on there, and it gives a puff of smell of
Are you
cooking
serious?
bacon.
Yes.
Yes.
Does
That will
wake
get you
people
out of
up?
bed. What?
Does that wake people up?
Well, it'll wake me up.
Yeah.
It wake Bulkley up.
You smell
He likes bacon.
Hey.
You have one right now. Where's the bacon? I'm not touching bacon.
All right. Anyway, back to this.
Very good.
I know hydronium. I know Kw, but I don't know OH, so I'll rearrange it. OH is going to equal Kw over hydronium. And yes, I need to see the work. It's the only reason some of you passed that last test, because I gave you partial credit.
73, baby. 73. This is good.
This guy here is.
Jesse barely passed.
Don't take Chem 2.
Mm-hmm.
It's horrible.
Mm-hmm. All right.
All your folks are today.
Yeah.
Dashing. I'm the dream squasher.
Yeah, that's it.
All right, look. So you see what I did here. Now the third reason that this guy's harder, besides the fact that you have to remember he reacts with it, you've got 2 of them. There's a third reason. I can't do this in my head. I'm going to have to get a calculator out and divide them out. Do that right now. Hurry up.
No,
Come on.
But my calculator-
Come on. Hurry up. We don't have all day.
I don't have a calculator.
We have 7 minutes.
Exactly. That's why I'm saying hurry up. I told you I was going a little faster because I knew I wouldn't have a whole lot of free time here.
I don't have a calculator.
So when you plug all that into your calculator, what do you get for your OH concentration? Olivia, what'd you get?
1.56 times 10 to the negative 12.
Anybody else get 1.56 out of 10 to the negative 12?
Yeah.
Yes.
All right. That's your concentration of OH. So I now know the hydronium and I know the OH. Here's another mistake you can make. Don't plug the wrong one into the pH calculation. pH is the negative log of the hydronium concentration, correct? So it's the negative log of which number? Right. In this case, it's the first one. Last time it was the second one we did.
Yeah.
But it's always the hydronium, which is the negative log of 0.00640 molar. Okay, do the math for that. Again, this is something you're going to really, I know a lot of you didn't bring your calculators first day of the chapter, probably forgot. You're going to have to get used to your calculator, just like you had to get used to the last one on the quadratic formula one. You have to find the log button on it. You probably haven't used it very often. You're going to find out whether some of them you plug the number in first, then hit log. Others you hit log and then the number. And don't forget, when you get that number, 0.00640, you take the negative of it, which makes them positive. What'd you get? Nick?
2.1.
2.1 what?
All right, fine. You want to go through decimals?
2.19? All right, 2.19 is the pH, is that correct?
Yes.
2.19.
All right. If that's the pH, what's the PLH? It's just going to be 14 minus 2.19, right? Right, because they have to add up.
11.8.
So
81.
11.81, okay? And that's your POH.
Wonderful. God, these problems are so much easier.
Yeah, I know.
It'll get harder though.
It will. These actually are the same exact kind of problems you saw back in Chem 1, but they are going to